atoms to memorize. And I'm sure you will get so familiar with carbon anyway that you won't even have time to force yourself to memorize this. Let's just start working with it and see what happens. So, we left carbon with 4 electrons in its valence shell. It's pretty bummed out. He's only got 4 and he wants 8. And he won't be happy until he has 8. He can't just take electrons from things because that would give him a really big charge. And I didn't mention this before, but a charge is kind of a stressful thing for an atom to take on itself. Sodium and chlorine were different. We'll talk about that why later in the second video with how atoms deal with stress. But if carbon were to just take 4 more electrons, that'd give him a really huge negative charge. So he can't take on that stress. That's ridiculous. So instead, he finds out about this scam called the covalent bond. You can sort of hear it, what this bond is about in just the word covalent. We are getting to get close with some other valence shells. Covalent. So another atom comes up to carbon who is looking for the same thing, a full valence shell. I'm just going to draw the electron out here. Now the scam of a covalent bond is that these 2 electrons will pair up. What does carbon get out of this? Well, he gets to keep his original electron over here, and now he gets to feel like he owns this one too. He feels like he has an extra electron. So now, even though carbon still has 4 original electrons, he went from feeling like he had 4 to now feeling like he has 5. Now what's the catch? Because I did mention that this was kind of a scam. The catch is that carbon can't leave whatever atom is on the other side of this deal. And I really mean can't leave. This is a strong bond. Remember we talked about ionic bonds? Well, organic chemists respect the covalent bonds so much that they represent this with a solid line. This carbon isn't going anywhere, and neither is whatever is on the other side of the steel. Carbon is essentially a sucker. But carbon doesn't really care about that right now. He's so desperate to feel like a rich guy with 8 electrons in his valence shell, and that now that he has figured out this covalent bond quick fix, he's pumped. In fact, he's so pumped that he is going to do the same thing with his 3 other electrons 3 more times. He's going to make 3 more covalent bonds. Check it out. I'm going to draw these bonds here, and he's got 4 scams going at the same time. Now he's really not going anywhere at this point. So he feels like a noble element. He's got the original 4 electrons he had, and now from each covalent deal he's running, he feels like he has an extra 4. That's 8 electrons. Merry Christmas, carbon. Don't shoot your eye out. Now before we meet some more atoms, I'd like to point out that carbon has a lot of options in getting his 8 electrons. Let's say he made a deal with 1 atom, then made another deal on top of that. He's giving 2 electrons to this atom over here, and carbon gets to feel like he has 4. 2 more than he had originally. This here is called a double bond, and it works just like a single bond. It's just 2 deals going on with another atom, the same atom. Now we can have a double bond over here, and 2 single bonds over here, and carbon still feels 8. 2, 4, 6, 8. With carbon's original 4 setting up 1 double bond and 2 single bonds. Maybe carbon wants to do this with 2 double bonds. 1, 2, 3, 4. The electrons it feels are 2, 4, 6, and 8. Still works. Maybe carbon wants to do a triple bond. How does that work? It works just like a double bond, except carbon really trusts this other atom that he's working with. So much so that he gives 3 electrons to this atom and makes 3 single bonds. 3 deals with 1 atom. And then you have 1 electron left over, so he has to do a single bond over here. What about a quadruple bond? Can carbon make 4 bonds with another atom? Sadly, that doesn't exist. Why not? Because there are only 3 dimensions in space that we can work with, leaving out string theory. We're going to get to what double and triple bonds have to do with 3-dimensional space later when we talk about orbitals. But basically, know this: when you're setting up carbon's bonds, you can't exceed 4, whether that's 4 single bonds, 1 double bond, and 2 single bonds, or 2 double bonds, 4 bonds in total, because it can't feel like it has less than 8 or more than 8, and it can't have less or more than the 4 original electrons it started with. So that's carbon's get up. And now that you understand this whole covalent bond scam, it should be easy to see why molecules form. It's all just a bunch of really desperate atoms trying to feel like they have 8 electrons. So they all find each other and set up this little network scam with each other, giving everybody else what they need. Sometimes the deal is only between 2 or 4 atoms altogether, making a small molecule, and sometimes the scam could even extend through 1 million atoms, like with proteins and things, really big molecules. It can be a whole neighborhood full of losers, but I shouldn't be hard on them. You gotta do what you gotta do. So, let's meet another atom. This here is nitrogen, an N. Nitrogen is just one click over on the periodic table, giving it 5 electrons in the outer shell. 5 electrons that give all the action. I'm going to draw 5 dots around nitrogen. So, just like carbon, nitrogen is going to try out this covalent bond scheme so it can feel like it has 8 electrons. Unlike carbon, nitrogen does not have a lot of options because of these 2 electrons. That's just the math. Nitrogen can only make 3 bonds in 2 combinations. One here is just 3 single bonds. This one is a lot more common, so get to know this. You have 3 single bonds, so nitrogen uses 3 electrons to feel like it has 6 electrons. Plus you have the 2 over here that we didn't touch. Feels 8 still has only 5. You should be getting used to the math here. If you want to count how many electrons an atom feels, you count the bonds as 2. If you want to see how many electrons it actually owns, you just count 1. Whichever one you're doing, single unbonded electrons are just counted as 1. The less common arrangement of nitrogen down here is 1 double bond and 1 single bond. You have 2 bonds going to 1 atom, 2, 4, and then a single bond to another, 6, and then the 2 left over, 7, 8. Feels like 8, still actually has 5. So that's nitrogen. Pretty easy. Easier than carbon anyway. So why don't we do an easier atom, just to roll with the momentum we have going here. This is hydrogen. Here is how simple hydrogen is. It only has 1 electron, period. 1 electron that makes up its valence shell, which is, well, its only shell. You may be asking, how the heck is it going to have enough bonds to feel 8? It's not. Remember, we mentioned how 2 electrons is like the mini Red Ryder BB gun that atoms will settle for if they're small enough. That's what hydrogen's going to want. He wants 2 electrons in his valence shell. If we look back at the neighborhood, hydrogen's rich neighbor over here is helium. Helium has 2 electrons, so it's happy. He's in the noble column, the things that don't react, because they already have everything they need. 2 electrons is sitting pretty. So that simplifies hydrogen's options. Since it wants 2 electrons and has only 1 covalent bond should do the trick. That was easy, right? Has 1 electron, feels 2. Alright. Only 2 more atoms to go. Up next, this guy here is oxygen. He is in 1 space to the right of nitrogen, which had 5. So oxygen has 6 electrons in its valence shell. I'm going to draw 6 dots around oxygen, like what we were doing before. And a lot like nitrogen, oxygen doesn't have a lot of options to choose from if it wants to feel 8 electrons. He has 2 options. I'm going to draw them here. He can either form 2 single bonds. We got 1 on the left and 1 on the right. These 4 electrons are just going to have to hang out here. So, oxygen uses its original 6 it has to work with. 1, 2, 3, 4, 5, 6, and with this arrangement it feels 8. 2, 4, 5, 6, 7, 8. Looks good, right? The second configuration we can do is just 1 double bond. That's 2 bonds going to 1 atom. Then 4 electrons hanging out on top here, like a hat. Uses 6, 1, 2, 3, 4, 5, 6, feels 8. 2, 4, 5, 6, 7, 8. Alright, 4 atoms down. One more thing to deal with here. We're going to kind of combine 2 atoms in 1. Sometimes in organic chemistry you deal with sulfur. I'm not going to teach you about sulfur as a new atom because it's really not that important. If you look at our table, sulfur is directly 1 click below oxygen. That means they have the same amount of electrons from their valence shell, 6. Counting from the left for oxygen, 1, 2, 3, 4, 5, 6. And counting from the left with sulfur, doing this